Hello guys, nice to see you. Sorry for the delay, was some technical issue. Apparently after this fall break, my computer didn't want to work properly. So how are you doing guys? How was your fall break? Did you manage to relax a bit? Good, that's important. Now the weather is not so nice anymore, but that's expected. Okay, so we finished before the fall break. Yeah, hello everyone who just joined. Nice to see you. So we just finished before the fall break our one of our topics, which is gravity. And today we proceed further with our next topic, which is oscillations, mechanical waves. So today we will introduce the harmonic oscillations, which is the building block of all types of oscillations and the key to understanding the mechanical waves. Will derive equations which describe harmonic oscillations, also describe velocity, like derive equations for velocity and acceleration of a particle which follows some harmonic oscillations, and discuss how some basic characteristics like period of harmonic oscillation, will give it definition, and how period of harmonic oscillation is determined by parameters of a system spring mass attached to the spring. Okay, so I guess with this we can start. Let me switch to the slides. Hope it works. Okay, looks like it works. Any periodic motion is some repeating motion of an object, which continues to return to a given position in space, for instance, after a fixed time interval. So there is some so-called period of this periodic motion, and that is a fixed time interval. So this object which undergoes periodic motion has to periodically come back to some given position. As I mentioned, we will focus on simple harmonic motion, and that is the key building block of all periodic motions. We will definitely need to understand the quantitative description of simple harmonic motion in order to proceed further with understanding mechanical waves. So ideal system for considering simple harmonic motion is a system string mass. So let us consider such system. We have a string with attached mass to it. So we have mass m. There is some string coefficient k. And let us assume that at initial position of the mass, is some a, capital A. So here is coordinate x. At t equals 0, the string is stretched and there is some displacement from the equilibrium condition 0. So obviously there will be some string force which will try to push this mass, like pull this mass back to the initial position. And this can be given as, so this Fs, S string, is equal to minus Kx in general, but we can substitute instead of X, A, if we want to be specific to this particular case. So the direction will be from the right to the left of this force Fs. Now, if this string shrinks so that the mass is at equilibrium condition, there will be no string force. Fs is equal to 0 because there is no displacement of the string and mass, and it can continue moving, so it will stretch, compress the string further. So eventually it will come to some position minus A. We assume that there is no friction, no dissipation of mechanical energy, some ideal isolated system spring mass. And here the spring force will be in the direction pointed from left to right. So now we know the force which acts on the block attached to this spring as a function of position. And we can, by using second law of motion, write the following equation. Minus k times x is equal mass of the block, because we consider that mass of the string is 0, times acceleration, a. So in this case, it's acceleration along axis x, the one-dimensional case. From this equation, we can express acceleration, which is minus a divided by mass m times x, which is displacement. So we see that from this equation, the acceleration of this block is proportional to its position. So it increases with x. And the direction of the acceleration is opposite to the displacement, because we have this minus here. So technically, this is the description of a simple harmonic motion. In order to realize simple harmonic motion, there should be this conditions of this motion should satisfy this equation. So acceleration should be proportional to the displacement, and the direction of the acceleration should be opposite to the displacement. So now we need to consider some differential equation, which is applicable for this particular case. Try to solve it, and that will be the way how we derive the equation of simple harmonic motion. So we want to get x as a function of time. So we want to know how position of this block will change with time when it undergoes simple harmonic motion. So let us recall that acceleration is equal to first derivative of velocity over time. But as you see, we have here x in the right side of this equation, and we want to know x as a function of time. So we need to make one step further and express acceleration as a second derivative of position over time. So in this case, let us write the differential equation. So it will be d squared x over dt squared equal minus k over m times x. So we can rearrange it. It will be d squared x dt squared plus k over m times x. And this is equal to 0. So this is a second order linear differential equation. And there are some very clearly defined rules and steps how we need to approach it in order to get the solution of such equation. So first of all, we need to define the type of differential equation, in this case, second order linear differential equation, and then follow very clear rules how to solve it. So in this particular case, for this type, we need to establish like some so-called characteristic equation and solve. We will consider that dx over dt derivative, let's substitute it with lambda, and then based on this substitution, we can write the characteristic equation. So in this case, characteristic equation will be lambda squared because we have second derivative of position over time plus k times m, which is coefficient next to x. So we don't write x because we characteristic equation is equation with respect to the derivative, not with respect to the function. So that is equal to 0. So now we have this characteristic equation, and we need to solve. So we see that it's some simple quadratic equation we need to solve with respect to lambda. So let us do it on the next slide.
Professor, why didn't we include x near k divided by n?
Why we don't include x? Yeah, it's a function. It's a function itself, which we want to eventually we want to know this function x as a function of t. So according to the rules how you form the characteristic equation, you should include there only derivatives of the unknown function and not unknown function itself. So we now form this characteristic equation, solve it. We define how this look at the solution of the differential of the characteristic equation, and based on the solution of this characteristic equation, we will see in which form we will get the answer for x as a function of t. Don't ask me why it is this way of solving differential equation of this particular type follows this procedure. That is like pure mathematics. So our goal is to identify the type of differential equation and know procedure how to solve it. And maybe in more in-depth explanation why you specifically solve this equation in this way, not in another, or why some specific approach to solve this type of equations is commonly accepted, I believe that your professor of mathematics can explain this much better. So my goal here is to show the solution, so you feel and see the whole process of solving this simple second order linear differential equation. But we definitely don't go here deep into the mathematic point of view. So we have a quadratic equation, which is lambda squared plus k divided by m equals to 0. And let us solve this. So we know, let's go for general case when we have discriminant, and here is discriminant is b squared minus 4ac. And here BAC, these are coefficients next to x squared, x, and just some numerical component of a general quadratic equation. So we can write something like a times x squared plus b times x plus c, that is equal to 0. So it's general form of quadratic equation. Here we can see that next to b, next to x, like we don't have x, so b is considered to be 0. And that's why we have just 4a times c. A is unity because next to lambda, we solve this equation with respect to lambda. We don't have any coefficient, so a is unity. And we have this c, which is k divided by m. So eventually, this will be minus 4k divided by m. So now we solve this with respect to lambda. For lambda, we have 1, 2. We have 2 solutions for quadratic equation. And in general form, the solution, as recall from your school program, minus b plus minus square root of discriminant divided by 2a. A is unity, b is 0. So what we get, let's write it here, 0 plus minus square root of minus 4k divided by m. And here we divide by 2 because a in our case is unity. So we get the following. We can take out this 4 from the square root. It will be 2. Then we cancel this 2 with 2 in denominator. And we end up with plus minus square root of minus k divided by m. So here we have minus under square root. That's why we need to operate with a complex number. So we have plus minus I times square root of k divided by m. And here I stands for square root of minus unity. So we got the solutions for this quadratic equation, which is characteristic equation of our second order linear differential equation. And we got it in a complex form. So according to rules, how you solve these second order linear differential equations, if you get a solution of its characteristic equation in complex form, then the general solution for the differential equation can be written in the following form. So we are interested in x as a function of t. Then our solution should be for this initial differential equation should be C1, which is some constant, times cosinus, oops, sorry, it's not sinus, cosinus square root of this solution of like real component of the numerical value of the complex solution of characteristic equation. So it will be k divided by m times t plus c2 times sinus square root of k divided by m times t. So this is the general form of the equation, which can, under different boundary conditions, satisfy our answer for x as a function of t. So that's exactly what we want. However, we have these constants and they are unknown because it's general solution. So we need to apply our specific boundary conditions of our considered case in order to get final form for x as a function of t with all terms which are included there, which are known to us. So first step, we can substitute this square root of k divided by m with omega. So we can make rewrite our equation in a bit more compact form. So it will be, let us do it on the next slide. X as a function of t is equal to C1 times cosinus omega t plus C2 times sinus omega t. So now we have this general form of solution for our differential equation, and we need to apply boundary conditions. Boundary conditions are the following. Let us consider t time equals to 0. As you remember from our figure at the beginning, the displacement, like x, was equal to a, some capital A, some amplitude value for the displacement in this case. So it was maximum displacement at t equals 0. So let us substitute this into our general solution, and let's see what we get. So x is equal to a, so instead of x as a function of t, we just put a. That is equal to C1 times cosinus omega t, and now it is 0. So we can probably just write cosinus of 0 plus C2 times sinus of 0. We know that sinus of 0 is equal to 0, and cosinus of 0 is equal to unity. From this, we can write that C1, the constant next to cosinus, is equal to A, to the amplitude of the displacement, amplitude value of the displacement. So first step is done. We already know one constant. However, there is still second remaining. and we need to apply some other boundary condition, which will allow us to get this unknown constant C2. Let's say if we consider the same time, t is equal to 0. From your point of view, what else we can, what other statement we can make based on this system spring mass attached to the spring, which could be helpful on the way of determining this unknown constant C2. We know that at initial point t, x is maximum, means that it reaches the maximum value and it doesn't move. So it means that the velocity of the block is 0. So we can write that v is, which is equal to the first derivative of the displacement over time, is equal to 0. So we have at t equals to 0 maximum displacement, and also true that at t equals to 0 our block doesn't move. It starts moving only at the moment when we start to count time from 0 to some interval of time. But at the initial moment, it doesn't move. So that is another boundary condition which can be useful for us. So what does it mean? That means that the derivative of this general form for the solution of our differential equation over time, first derivative over time, should be equal to 0 at t equal to 0. So in order to get some benefit out of it, let us first take the derivative. So dx over dt, that will be, we know that derivative of cosinus is equal to minus sinus, and derivative of sinus is equal to cosinus. So first we have this term with cosinus, so it will be minus C1 times sinus omega t. Let's take it maybe in parentheses. And in addition, since we have function in the under sinus, so it's omega t, we need to take derivative of this and multiply. So it will be derivative of omega t over t will be just omega. So we multiply it by omega. Then we have another term, which will be here C2 times cosinus omega t, and again we multiply by omega. So now we have the derivative, and we set this derivative to 0. Maybe let us write it separately so it's not so confusing. At t equals 0, we get the following: minus C1 sinus, here we can put 0 times omega, plus C2 cosinus 0 times omega, and that is equal to 0. So what we get here, sinus 0 is equal to 0, cosinus 0 is equal to unity. Since omega is not equal to unity, because we have some oscillations, means this angular frequency is not equal to 0. So omega is not equal to 0. And this term, so this term already is 0 because we have sinus 0. This term will be equal to 0 only if C2 is equal to 0. So that's why from here we can write that C2 is equal to 0. So we have already found two constants which were unknown, applying our boundary conditions. So C1 is equal to A, C2 is equal to 0. So now we can write the solution of our differential equation for our particular case, taking into account differential equation and its boundary conditions. That will be the equation for the simple harmonical motion. So that will be x as a function of t is equal to a, which is our constant c1, times cosinus omega t. So C2 is equal to 0. That's why we don't have this term here. To be more general, we need to write it in this form. It will be A, which is amplitude of the displacement of the particle which undergoes harmonic oscillation, times cosinus, and here will be omega t plus phi. So phi is some phase constant and determines, it takes into account cases when our oscillation doesn't start from the displacement equal to A, but a bit smaller displacement. So if we have initial displacement equal to A, then at t equals to 0, then this constant, phase constant phi should be equal to 0, and we have just this equation which we got in our derivation. However, we can start our oscillation from any point, and this p, which is phase constant, can take this into account in order to get the equation of harmonic oscillation in the most general form. So now, next step, since we know the position as a function of time of a particle which undergoes harmonic oscillations, next step would be to determine its velocity as a function of time and acceleration. So let us do it. Maybe let's write again this equation for x is equal to A times cosinus omega t plus p. And now the question is, how do we go from this to velocity and acceleration? As a function of time. Any suggestions?
Is the derivative?
Sure, you are right. We need to take first and second derivative of this function over time in order to get unknown velocity as a function of time and acceleration as a function of time. So let's do for velocity, we take first derivative over time. That will be minus, because so here is cosinus, we will take derivative, it will be sinus. Here we have also omega times t. So we will get minus omega times a times sinus omega t plus phi. So that will be for velocity. And in order to get expression for acceleration, we can write here as a function of time, make it clear. We take the second derivative, so it will be dv already over dt. So we take derivative already from this equation. So that will be minus omega square, because we have already one omega here, and then we will get one more. So it will be omega squared times a times cosinus omega t plus phi. So these are three equations which describe kinematics of the simple harmonic motion. So it provides us the function of the displacement, velocity, and acceleration of this particle which performs simple harmonic oscillation as functions of time. So from these equations which describe velocity and acceleration, we can see that they possess some maximum values. So these coefficients here, which stand before sinus and cosinus, they actually give us, because sinus and cosinus can change from 0 to unity. So that's why the maximum values which velocity and acceleration can get, they will be defined by these coefficients in front of sinus and cosinus. So we can write that so V maximum is equal to omega A, and instead of omega we can get this, substitute its expression, it will be spring constant K divided by mass of the block times amplitude displacement A. And for the maximum acceleration, we can write that it's omega squared times A equals to, we can here get rid of this square root. So it will be K divided by M times A. So these are expressions for the maximum velocity and acceleration, which can be achieved by the particle under this particular harmonic oscillation. So there is another parameter which we should highlight, and this is the period of this motion. Period is capital T, and this is time interval during the during which particle goes through the whole cycle. So it means it comes back to the initial stage, and that means that these parameters which we for which we derive the equations, displacement, velocity, and acceleration of this particle at the phase omega t plus phi is equal to the same parameters at the phase omega t plus period capital T plus phi. So that means if we have a difference between the phase, let's say this is phase 2, this is phase 1. So here will be omega times t plus period plus phi, let's take it in such square brackets, minus first phase, which is just omega t plus phi, also square brackets. This will be equal to 2 pi. Means that their full cycle has been done and the phase of the harmonic oscillation changed by 2 pi. So it just came back to initial stage with the same values for displacement, velocity, and acceleration. So from here, we can write that omega times t is equal to 2 pi. And as easy to see that the period is equal to 2 pi divided by omega, the angular velocity. This is angular frequency. So we know that angular frequency is given as spring constant divided by the mass of the block. And thus, if we substitute it here instead of omega, we will get expression for the period of this harmonic oscillation of the spring block system as 2 pi times square root of m divided by k. Also, we can write for frequency. So let's write maybe here, we have some spot here. Frequency is equal to 1 divided by period t, 1 over t. And then, so means frequency gives us the number of full cycles of this harmonic oscillation, which happens in the time interval of 1 second. And that will be equal to 1 over 2 pi times square root of k divided by m. So these are main characteristics and equations which describe simple harmonic motion, which we derived during this discussion. And for today, that is everything what I wanted to tell you. So any questions regarding this topic? You're welcome. So we started with the second law of motion, defined this differential equation, which is second order linear differential equation, solved it according to rules for solving these types of differential equations, got the expression for the displacement as a function of time, which means we got the equation for the simple harmonic motion. Then taking first and second derivatives over time of this function, we get expressions for the velocity and acceleration as a function of time. And yeah, should be mentioned that we got the explicit solution for our differential equation based on boundary conditions, which define our particular situation when at t equals 0, we get maximum positive displacement, and also at t equals 0, velocity is equal to 0. Based on equations for velocity and acceleration as a function of time, we got two equations describing maximum values for velocity and acceleration for simple harmonic motion, and also have shown how we can express period and frequency of simple harmonic motion in terms of mass of the block and spring constant of the spring this block is attached to. Okay, that is the main message and conclusion of our today's discussion. We will continue discussing periodic motions and like simple harmonic motions next lecture, which will be on Wednesday. So thank you very much for attention and see you on Wednesday.
Thank you. Bye.
Okay, bye-bye.